Hey guys, I wanted to go over this individual problem because I thought it was interesting and useful, and it seems like something that could show up. And it has to do with the quantization of charge. So the idea that charge only exists in these discrete amounts, which is going to be the charge of an electron or a charge in a proton. So a scientist studying pollen collects many identical pollen grains of mass m. The scientist subjects the grains to a process that strips one or more electrons from each grain and then injects the grain into a vertical evacuated tube. At the bottom of the tube is a sphere carrying a charge Q equals 1 microcoulomb. The grains in the tube subject only to the forces of Earth's gravitational field and the charge Q grouped together when they come to equilibrium as shown in the diagram to the right. The numbers in that diagram represent millimeters of distance. So we have some here, some there, some there, and some there. So why do they do that? Because charge is quantized. Each individual location represents an integer times the elementary charge extra charge. So charge only exists in 1e, 2e, 3e, dot, 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 dot. Draw a diagram of the force exerted on a single grain and use the diagram to write an equation that expresses the exerted force in terms of m, q, and y. So we would have mg going down, and that's 4 down. I'm going to have fe going up, that's 4 up. And so we would have k, q, q over, I did h, but they used y. Y squared is equal to mg. Using the diagram given in the scenario, fill in the table below with the charge Q on a single grain and a height y of a single grain. Note that you are asked to calculate y squared. So we have k, q, q over y squared is equal to mg. Okay, so I'm going to get q by itself, so I can get that value. And that's going to be equal to mg y squared over kq. I have a paper over here. Why don't I grab it so I'll be able to see the value, so I can work along as this goes. So I can read off this paper as we're doing this. So I'm not going back and forth every 2 seconds from one to the other, right? All right, so our first one, it looks, is at 4.4. millimeters. So that would be 4.4 times 10 to the negative third. Our next one looks like it's at about 6.1 times 10 to the negative third millimeters. Our third one looks like it's at 7.5 times 10 to the negative third. meters. The next one looks like it's at 8.7 times 10 to the negative third. And the last one looks like it's at 9.7 times 10 to the negative third. So let me square these real quick because I need to square it anyways for my values. So I have 1.9 times 10 to the negative fifth. .7 times 10 to the negative fifth. I'm not going to add, even though my calculator's giving me extra, I'm just going to put, I only have 2 units there, so I'm not, 2 digits. I'm not going to add any extra digits in there. I have 5.6 times 10 to the negative fifth. I have 7.6 times 10 to the negative fifth. And I have 9.4 times 10 to the negative fifth. Now I need to solve for Q for each one of these. I know that M for every single one is okay, so I know that big Q is 1 times 10 to the negative 6. I know K is 9 times 10 to the 9th. And then this is going to be our elementary charges. And again, this can only exist in increments of 1.6 times 10 to the negative 19. And they want me to graph Q squared versus Y squared. I'm going to make this smaller so that it is easier for me to deal with. So whatever they say is on the first is your y-axis, second is your x-axis. You get a little bit smaller, huh, to fit it all in here. So on the one side, I'm going up. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 20. And my biggest one is 8. So I can make each one 2. So I'm going to go 2, 4, no. 2, 4, 6, 8. Yeah. So 2, 3, 4, 5, 6, 7, 8. And then at top, I'm going to say times 10 to the negative 19. I'm going to say this is Q in coulombs. And then along the x-axis, I go up to 9.4. And if I have 10, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is going to be times 10 to the negative fifth. I'll put at the end down here. And then my units are meters squared. So I'm going to label it and do meters squared. All right, so let's plot our points. I have 1.6 and 1.9. So it's 1.9 over, it's 1.6 up. Second point, I have 3.7 and 3.2. So 3.7 over, 3.2 up. Third one, I have 5.6 and 4.8, a little bit past half. Then I have 6.4 and 7.6. So 7.6 over, 6.4 up. And then my last one, I go 9.4 over, so almost to 9.5. And I go 8 up. All right, so I'm going to draw a best fit line. Yours is going to be better than mine, because you can be able to use a ruler. And then I'm going to pick 2 points that are on my line that are not my points for my points. So I have 1 times 10 to the negative 5th, comma 1 times 10 to the negative 9th. And I have 7.5 times 10 to the negative 5th, and I have 6.5 times 10 to the negative 9th. All right, so we're saying I want to get m from this. I know that k, q, q over r squared, which is y squared, is equal to mg. So my slope is going to be q over, I should say y, not r, right? Q over y squared. So they told you what to graph. Get this stuff over here. So we're going to have our y-axis, our x-axis, and then we'll have mg k over q there. So our slope is going to be equal to mg k over q. My shoe is messing up. All right, so I'm going to do 6.5 minus 1 times 10 to the negative 9th coulombs, and I'm going to do 7.5 minus 1 times 10 to the negative 5th meters squared. And you should have substitution with units for this. So I have 5.5 times 10 to the negative 9th divided by 6.5 times 10 to the negative 5th, which is going to give me 8.46 times 10 to the negative 5th coulombs over meters squared. This is equal to mg kq. So m would be equal to kq times this. So 9 times 10 to the 9th newtons meters squared coulomb squared. Q, which is 1 times 10 to the negative 6 coulombs times the slope, which is 8.46 times 10 to the negative 5th coulombs over meters squared, divided by 10. And I got 0.076 kilograms. So 7.6 grams. All right, what else do they ask us? Let's go on to the next slide. Explain how you use the equation from part B to determine the meaning of the slope of the graph by giving the relationship between the mass and the slope of the line above. So I manipulated the equation to show the slope on one side. So KQQ over y squared equals mg. So Q over y squared equals mg over KQ. This is the slope. Then I isolated m. So I'm saying the slope is equal to mgkq. So m is the slope times kq over g. Then I substituted in numbers and solved.